everyone, and welcome back. Today we're going to be continuing our exploration of real analysis and begin our journey of functions whose domain is the set or subsets of real numbers. For the past several discussions, we've been primarily focusing on sequences whose domain is the natural numbers or potential subsets thereof, but now we're going to try and extend those ideas to more broader classes of functions, in particular functions of real variables. So what I want to do to introduce the concept of limits of functions is to revisit what we mean to be a limit of a sequence. So remember that if an is a sequence of real numbers, then we say that the limit of that sequence is equal to alpha, and obviously alpha a real number, if for any epsilon greater than 0, there exists a natural number n such that for all little m bigger than big N, the distance between our sequence values and that potential limit value is arbitrarily small, in particular less than some given epsilon. Now, the definition for the limit of a function is actually very similar to that, and it goes as follows. So we're going to be taking a mapping f, which maps a, which is going to be a subset of the real numbers, whose range is in the set of reals. So this is a little bit different compared to that of sequences, whose domain is the set of natural numbers, right? So now we're going to be placing a bunch of objects, not necessarily natural numbers, into this mapping, right? But we're still going to be mapping to the set of real numbers for our codomain. Then we say that f is said to have a limit at x is equal to a. So this is a little bit different compared to limits of sequences, which in some sense are just limits at infinity. But we can have a limit at any point a in the set of real numbers, and in particular, a doesn't have to belong to the domain. That's important to note. So we will say that the function has a limit at a, for which we will write the limit as x approaches a of f of x is equal to L, so L is our limit, and obviously L is going to be a real number, if, and then here comes the similarity with the sequence definition, for all epsilon greater than 0, there exists a positive number delta, so this is similar to our positive natural number capital M, such that if the distance between x minus a is arbitrarily small, right? That's why we require that absolute distance to be greater than 0. So we don't want x and a to be equal to each other. So if you choose any x in the domain of f, and the distance between that and the limit value domain is arbitrarily small, in particular less than some delta, then the distance between f of x and its potential limiting value is also arbitrarily small as well. So if we think of this from a geometric perspective, so here we have some function, let's call it f, whose domain is in the set of real numbers, so that's practically our alpha values. And let's assume we're interested in finding the limit as x approaches a. So we grab a neighborhood around a, so this is going to be a minus delta and a plus delta. So that's just some neighborhood around a. So if we sort of map to the values in the range of that, keep in mind if a is in the domain, as long as a minus delta and a plus delta is in the domain as well, then we can map them to an element in its range. So that means the point that this a projects to, keep in mind that could be an open circle that belongs to the codomain, potentially, of this function is said to be the limit, right? So there's our L plus epsilon on the top, and there's our L plus epsilon on the bottom, right? So as this interval in orange gets arbitrarily closer to A, this interval, this vertical interval that is in green is going to get arbitrarily close to L. And if as we squeeze this distance between our domain value and the domain limiting value to be closer and closer to 0, then if f of x has a limit to be equal to L when x is equal to a, then that distance should also get arbitrarily small. All right, so let's see if we can go ahead and prove formally particular limits, right? So let us prove that the limit as x approaches 3 of 5x minus 7 is equal to 8. Now, of course, there are several algebraic properties of limits that you probably already know from single variable calculus. For example, you probably already know that 5x minus 7 is a continuous function. Therefore, the limit value and the functional value are equal to one another. But let's not jump to conclusions, because sometimes that takes away the beauty of what limits actually are. Because it's possible that this function is not even defined at x is equal to 3, but it's still possible that that limit still exists, right? So being able to prove via the epsilon delta definition of limits, it does have its strengths. Right? So how are we going to prove that the limit is equal to 5 times 3 minus 7? So as we did with sequence limits proofs, we're going to begin by letting epsilon be greater than 0. And now we're going to look at the distance between this function and that proposed limit value. So that means the distance between 5x minus 7 and 8 is equal to what? So let's just do a little bit of arithmetic here. So we have 5x minus 7 minus 8. What is that going to be equal to? So that's going to be equal to the absolute value of 5x minus 15. And notice, we do have a common factor of 5, so let's just factor that out. So we're going to have 5 times the absolute value of x minus 3. Now what's very interesting here is we have this absolute value of x minus 3, and 3 is precisely the value a that we're interested in finding the limit at, right? Because what we want is we want our absolute value of x minus a, in this case, to be arbitrarily small as well. So we have complete control over this distance, just like we had complete control over that capital M. Right? So we can choose this distance to be as small as we want it to be, right? Because we want this to be strictly less than 5 times delta. So if somebody gives you an epsilon, how are you going to choose your delta that depends on that epsilon? So what we can do is we can choose our delta to be equal to epsilon divided by 5. So when you have that this is going to be equal to 5 times epsilon over 5, which as we know is just going to be equal to not 5, but epsilon. Right? So we have that the absolute value between f of x and L is arbitrarily small. Right? So once we have that, that means that the limit as x approaches 3 of 5x minus 7 is indeed equal to 8. And that's how you prove formally limits using the delta epsilon definition. So let's go through a couple more examples just to make sure that we're comfortable with this process. So let's go ahead and see if we can show the following. So let us prove that the limit as x approaches 2 of x squared minus 4 all over x minus 2 is indeed equal to 4. Now, this example is slightly different because notice if we take our f of x to be equal to x squared minus 4 over x minus 2, we're trying to find or show that the limit as x approaches 2 of f of x is equal to 4. But notice that we can choose our domain to be equal to the set of all real numbers except for 2. So our limit domain value does not belong to the domain. But keep in mind, the limit domain value does not have to belong to the domain in order for this limit of the function to exist, right? So being defined at a point is not a requirement for the limit to exist, right? So that's very, very useful. Okay, so let's see how we can go about doing this. So as usual, we're going to be letting epsilon be greater than 0. So let's look at the absolute value of this. So we have the absolute value of x squared minus 4 over x minus 2 minus our proposed limit value of 4. Now keep in mind that 2 is not in the domain, therefore x squared minus 4 over x minus 2 is always defined, so we can do any algebraic manipulation on this and still have a defined value. In particular, we can factor that numerator into x plus 2 times x minus 2 divided by x minus 2, and since x minus 2 is never equal to 0, we do not have a division by 0 case, so we can cancel these out without having to worry about anything. So we're just going to be left with the absolute value of x plus 2 minus 4, which we know to be equal to the absolute value of x minus 2. So keep in mind, what are we trying to prove? We're trying to prove the limit as x approaches 2 of f of x is equal to 4. So our domain limit value is going to be equal to 2, and we have complete control over this thing, because we know that this is going to be less than delta, so we just need to choose a delta that makes this distance less than epsilon. So this is actually a very, very easy choice. We can actually just choose delta to be equal to epsilon, and then we're going to have that this inequality is held. So we have that the distance between f of x minus 4 is arbitrarily small, provided that would make the distance between x and 2 arbitrarily small as well. Right? So this proves that the limit as x approaches 2 of f of x is equal to 4. So that's actually very, very nice, and the proof actually isn't that complex. Now, actually, let's go ahead and do an example where the process is actually not as easy as those two. In particular, let us prove that the limit as x approaches 1 of x squared minus 5x plus 1 is equal to minus 3. Right? So 1 squared minus 5 times 1 plus 1 minus 3. So how are we going to prove this formally? So let's just start off, with the typical strategy and see where it goes. So as usual, we're going to be letting f of x be equal to x squared minus 5x plus 1. And obviously the domain of this mapping can be chosen to be the set of real numbers since we're working with a polynomial. So we're going to be letting our epsilon be arbitrarily small but positive, and then let's see what happens to the distance between f of x and L. So the absolute value of x squared minus 5x plus 1, and then we're going to minus our proposed limit value of negative 3, and that's going to be equal to the absolute value of x squared minus 5x, and then we have 1 plus 3, that's going to be equal to 4. Right? So what exactly are we going to do with this? So if we can factor this, that will actually be very, very useful, and indeed we can, because we know that that's just going to be equal to x minus, so how is this going to factor? So take a moment to think about it. We need two numbers that multiply together to give us 4 and add together to give us negative 5. So that's going to be x minus 1 and x minus 4. So what are we trying to prove here? So we're trying to prove that the limit, it looks kind of strange with two i's, so the limit as x approaches 1 of f of x, we're trying to show that this is equal to minus 3. So we're going to have complete control over the distance between x and 1, provided that x is in our domain. And by properties of absolute values, we know we can decompose this into the absolute value of x minus 1 times the absolute value of x minus 4. Okay, so what do we have here? So we know that this is going to be strictly less than delta, so we're going to have delta times the absolute value of x minus 4, but we do not have control over x minus 4. But notice that when we say that the absolute value of x minus 1 is less than delta, that means that x is practically equal to, but not equal to, exactly 1. Right? So for example, we can take any x value, for example, in between 0 and 2, and see sort of what is happening to the absolute value of x minus 4 and see if we can actually bound that absolute value. So if we take a moment and analyze this curve x minus 4, what exactly do we have? So absolute value of x minus 4 we know is just going to be an absolute value curve whose vertex is located at x is equal to 4, and it's going to have this sort of V shape here. Right? So we know that when x is equal to 0, y is equal to 4, and we have this particular shape. So we know that when x is approximately equal to 1, if we take sort of a neighborhood around that, call it 0, 2, then practically everybody is hanging around this particular region for its input. So if that is the case, if we project 0 upwards, we're going to get 4. And if we project 2 upwards, we're going to have the absolute value of 2 minus 4, which is going to be equal to 2. So as long as x is somewhere near 1, that means the output is somewhere near 4, right? So we know that when x is close to 1, that means this object is less than or equal to 4, right? So that means this is going to be less than or equal to delta times 4. Right? And now it's very obvious as to which Delta we're going to choose, so we can choose our delta to be equal to epsilon over 4, and that's going to give us that this is going to be equal to epsilon, right? So that's going to give us that the absolute value of f of x minus 3 is going to be strictly less than epsilon, since we have our strictly less than there, and therefore we have completed the proof that the limit as x approaches 1 of x squared minus 5x plus 1 is equal to minus 3, using the delta epsilon definition of limits of functions. The next term that I want to introduce today is what is called a limit point, and I'm going to provide two equivalent ways to define a limit point. And also take note that some other people may call this a cluster point, some other people may also call this an accumulation point, but I'm just going to call it a limit point. So the first definition is as follows. So a point A in the set of real numbers is said to be a limit point of a set A, let's assume A is a subset of reals, if for any positive number delta there exists at least one point in A, except for little a, such that the distance between x and little a is arbitrarily small. Now, that definition is perfectly fine, but typically we're working in the same metric space R with the typical metric of absolute value of x minus y, right? So in some sense, it's a little bit more useful to view this definition from the perspective of neighborhoods. So an equivalent definition is the following. A point A is, again, said to be a limit point of A if for any neighborhood of A with radius delta, they always exist at least one point in A that is within this particular interval, except for A. Keep in mind that it's obvious that all neighborhoods of A contain A. That's why we're excluding A from this neighborhood. So let's do a couple examples to see if we can identify whether a point is or is not a limit point of a set. So let's assume that A is the open interval 1, 2, or equivalently all x in the set of real numbers such that 1 is less than x is less than 2. So is the point 1 a limit point of A? And you can use this definition, pause the video, and maybe try it on your own. So let's give this a go. So let's do a quick solution for this. So we're going to be letting delta to be greater than 0, and we're going to build a neighborhood around 1. So we're going to look at the neighborhood of radius delta around 1, which is obviously going to be equal to 1 minus delta and 1 plus delta. So let's draw a little picture here. So what does 1, 2 look like? So 1 is here, 2 is here, and this is obviously open neighborhoods. So what we're going to do is we're going to be building a neighborhood around this point. So this region is our n delta of 1, and there has to exist at least one point in this neighborhood in order for this to be considered a limit point. Keep in mind, delta is an arbitrarily small but positive number, but indeed it is positive, right? So that means that 1 plus delta is not equal to y, or delta, right? So 1 plus delta and delta are not equal to each other, right? And we do know by properties of real numbers that 1 plus delta all over 2 is going to be strictly between. So it's going to be strictly between, actually, what do I want to do? I want to do 1 plus delta and 1, right? So I'm just finding the average of this point here and this point here to get a point in between 1 and 2, which is belonging to my point A, because we just need 1. I'll just point in A, take away little a. So if I do this, what do we have? So that's going to be equal to 2 plus delta over 2, and that always belongs to the interval 1, 2, right? So since we can always find a point in between that for an arbitrarily small neighborhood around 1, that means that 1 is a limit point of the open interval 1, 2, right? Do you get the hang of it? So let's see if you can prove or disprove the next statement. So let's assume we have the interval B, which is actually just going to be the set containing 1 and 2. So it's a union of two singleton sets, 1 and 2. So is 1 a limit point of B? Right? So again, pause the video and see if you want to try this on your own and see if you can come up with a nice solution for this. So we're going to be letting delta, again, to be positive, and we're going to consider a delta neighborhood around 1. So as usual, we're going to have 1 minus delta, and then we're going to have 1 minus delta. So if we sort of draw our real axis here, so I'm going to do a dotted line because we only have the numbers 1 and 2 in here. So we're building our neighborhood around 1, and all we need is one point around this. And keep in mind, this has to be true for all neighborhoods, not just one. So keep in mind, it's possible that we build our neighborhood such that 2 is included to that. For example, just take delta to be equal to 50. Guarantee that 2 is going to belong to that neighborhood. But that's just one interval, and it has to be true for every neighborhood. So if you want to show that a point is not a limit point, all you have to do is just find one delta such that any other point, aside from the center point 1, does not belong to that interval, right? So if we, for example, take delta to be arbitrarily small, notice that 2 will not belong to that interval, right? So let's just take delta to be equal to 1/2, and that's going to force our neighborhood to be equal to 1/2 and 3/2, right? And since the only other point in that set, right, because keep in mind 2, that's the only other element point, right? So we can take 2 to belong to the set 1, 2, excluding 1. But this point does not belong to this particular 1/2 neighborhood. That means what? So we find a neighborhood that does not contain at least one other point. So that means that 1 is not a limit point of the set 1, 2, right? So it's a sad day for that point, isn't it? Now let's introduce the first theorem that I want to talk about today, and it says the following. Let's assume that f, again, maps A to R, where A is a subset of the reals, preferably not the set of naturals, else we'd be dealing with a sequence. And let's suppose that little a is a limit point of A. Then we say that the limit of f of x as x approaches A does not belong to R. So some people will say that the limit does not exist if and only if, right? So this is very, very useful. There exists a sequence that is entirely contained in our domain of our function with an not the constant sequence equal to the limit point that satisfies the property the limit of an is equal to A. And it should be very straightforward that the limit of a constant sequence containing only A has A. So that's in some sense one reason why we exclude that from our choice. And if we evaluate the limit of the sequence of f composed with an, if this does not belong to R, but the limit of the individual sequence is equal to A, then that is enough to justify that the limit of our function as x approaches A does not exist in the set of real numbers. So this theorem pretty much gives us tools in order to establish the lack of existence of a limit of a function. So let's see if we can go ahead and prove a very common example of this limit. So let's look at the limit as x approaches 0 of 1 over x. So the claim is as x gets arbitrarily small or close to 0, this does not get close to a real number or does not exist in some sense. Right? So how are we going to prove that the limit of 1 over x as x gets close to 0 does not exist? Okay, so what do we need to do? So we're going to need to choose a sequence in the domain of this function, but notice I haven't chosen our function, right? So obviously we're going to be letting f of x be equal to 1 over x with the domain of this relation to be equal to the set of real numbers except for 0. Okay, so we need to be choosing a sequence in this set, right? So as long as the sequence does not contain 0, then we're safe. So we're going to be choosing an to be equal to the sequence 1 over n, where n is in the set of natural numbers. And it should be clear to see that this is indeed a subset of r backslash 0, right? So that property is satisfied. Now we need to justify that the limit of this is equal to something. In particular, it needs to be equal to the value that we're taking as x approaches, right? So x approaches 0. So 0 must be the limit of this sequence, right? So the limit of an is equal to, as we already know, the limit of 1 over n, which we've proven at least 2 ways, is equal to 0, right? So this part satisfies. And if we can show that the limit of f of an does not exist, then we're good. That's right. So property 1 satisfies, property 2 satisfies. Now let's make sure the third property satisfies, right? So f of x is equal to 1 over x, which means that f of an will be equal to 1 over am. So if f of an is equal to 1 over an, that means f of an will be equal to 1 over n, which we know to be equal to n. So we have this particular sequence. So if we can show that the limit of this sequence does not belong to the set of real numbers, that means the limit of our function will also not belong to the set of real numbers. So how do we show that? So what is the limit of f of an? So that's just precisely the limit of n, the identity sequence. So we know that n is an increasing sequence and it's not bounded above, therefore that diverges. So therefore we have the limit of that does not belong to the reals. So since we satisfied these three criteria, then we have that the limit as x approaches 0 of 1 over x also does not belong to R. So that is the formal way to show that the limit does not exist. Now there are several other examples that you definitely should try on your own, and I'm going to give you a couple because they're actually quite useful. One of them is the limit as x approaches 0 of the absolute value of x over x. This is a very, very useful example because in some sense it gives you intuition about one-sided limits, because as x approaches 0 from the left, you get -1. As x approaches 0 from the right, you get +1. And since the left and the right aren't converging to each other, then of course this limit will not converge. But you can do practically a similar exercise as we did for 1 over x and still get the same conclusion. And if you were up for a little bit of a challenge, showing that the limit of sine of 1 over x squared not belonging to R also is a fun challenge as well, right? So those are just some things for you to explore on your own. Now that we have some notion of the limits of functions, now let's introduce the notion of one-sided limits, which we probably already have experienced in single variable calculus. So here's the formal presentation of it. So as usual, we're going to be selecting a subset of the set of real numbers, and let's assume that f maps A to R, so A is going to be the domain of our mapping. So we're going to be choosing A in the set of real numbers, and let's assume that it is a limit point of the set A intersection A infinity, so practically the right-hand side of our domain. Then we say that as x approaches A with an exponent of plus, some people will say the limit as x approaches A from the right-hand side of the function. So we say that this one-hand-sided limit is equal to L if, and then we have the definition of limit again. For all epsilon greater than 0, there exists a positive number delta such that for all x in our domain, if 0 is less than x minus a is less than delta, and notice that there is no absolute value on this distance because we don't want to the left side of x, we just want on the right hand side of x, right? So as long as the right hand distance of x, as long as that distance is arbitrarily small, right? So if we look at sort of a picture, if we look at, for example, our neighborhood of x, which is typically x minus delta and x plus delta. So if we look at our little picture here, x plus delta, and x minus delta. So we want this distance here to be arbitrarily small, and the left-hand side doesn't even have to exist for right-hand sided limits. Then, if that is true, and then for all epsilon we have that property, then we have the distance between f of x minus L is arbitrarily small, right? So as this right-hand sided distance gets arbitrarily small, as long as the vertical distance between f of x and L gets arbitrarily small too, then we say that f of x converges to L, or equivalently we say that the limit as x approaches a from the right of f of x is equal to L. And a similar thing can be said for a left-hand sided limit, or the limit as x approaches a from the left-hand side, as long as the left-sided distance is arbitrarily small. As long as that is arbitrarily small and produces an arbitrarily small distance in the vertical direction, then we say that the left-hand limit of f of x as x approaches a is equal to L. Okay, so if we look at a little diagram, to sort of illustrate this, so let's assume that we have this type of picture here. So let's assume that this is like 5 and this is like minus 3. And let's assume that this vertical line corresponds to x equals 0. Let's assume that this is x and this is f of x and this is f. So if we look at this particular picture, we see that the limit as x approaches 0 from the left-hand side, well, what is this going to be? So if we approach 0 from the left-hand side, all we need to do is just let this distance get arbitrarily small. So what happens to our distance? So if we project this upwards, we're going to have that distance is going to slowly converge down to 5, right? So using that definition, we have that this is going to be equal to 5, even if that circle is not closed. And similarly speaking, if we approach x to 0 from the right-hand side, then all we need to know is that this distance right here is going to be arbitrarily small. So this is going to converge to 0 in terms of distance, right? And what happens to our vertical values? So if we project this value down and look at this distance here, that distance is going to squeeze down into -3. So we're going to say that the limit as x approaches 0 from the right-hand side, that will be equal to -3, even if that circle is not closed. Okay, now, if this is well established, what can we say about the limit as x approaches 0 of this function? Well, when we looked at sequences, we already know that if it does converge, it converges to a unique limit. And here we're like, okay, well, from the left it's equal to 5, from the right it's equal to -3. But generally speaking, what would be the limit? Can we define the limit of functions to be equal to two numbers? Can it be both 5 and 3? Like, what do? Can we take the average of these two numbers? Like, what is our, what are the rules that we're bounded by? So using the delta-epsilon property for limits, you should be able to establish that the limit of functions is a unique number. And the proof of that's practically the same as we did with sequences. So it cannot be 5 and it cannot be 3. So is it possible that we choose one of them and define that? Actually, no. And the next theorem establishes what the actual result is. So theorem 2 says the following. So let's assume that A is a subset of the real numbers, and let's, as usual, take f and map it from a to r, and let's suppose that a is a limit point of, and let's assume a intersection a infinity, and also let's assume that it's a limit point for the set a intersection minus infinity to a. Because if a is a limit point for the left and the right hand side of our limit value a, that establishes that the right and left hand limits can both exist simultaneously, so we're safe, right? So when that is the case, then what happens when you have that the left and the right hand limits are not equal to each other? So this theorem says the following. So then the limit as x approaches a of f of x is equal to L if and only if the limit as x approaches a from the left, the limits as x approaches a from the right are equal to each other. So for our example, they weren't equal to each other. Moreover, they have to be equal to the same number, right? So you could take the contrapositive of the statement and say, okay, well, if the two one-hand-sided limits do not equal to each other, then we have the limit does not exist. Right? And keep in mind that you can also prove that the algebraic properties for limits do exist, so you can still use those properties with no big deal, but you can prove them formally if you desire. So let's actually look at an example of how we can use this limit to our advantage. So let's take the function f of x, which is equal to 3x plus 5 for x less than 2, and x squared minus 5 for x bigger than 2. Right? So my question to you is the following. Does the limit as x approaches 2 of this function exist? And if it does exist, what does it equal to? Right? So what do we have? Well, we have a line on the left and a parabola on the right-hand side of our domain, right? And obviously 2 is going to be a limit point for the left-hand side of the real line below 2, and 2 is also a limit point for the right-hand side of the real line as well. So limit points don't have any issues there. So how are we going to take limits? So let's look at the left-hand side. So the limits as x approaches a from the left-hand side is practically equal to the limit of 3x plus 5, right? So what is the limit of 3x plus 5 as x gets close to 2, right? So this is going to be equal to the limit as x approaches 2 from the left of 3x plus 5. So that's going to be equal to 3 times 2, which is 6, plus 5, which is going to be equal to 11. And you can prove formula using the delta-epsilon definition, similar to what we did before. And if we look at the right, so the limit as x approaches a from the right of f of x, this is going to be equal to the limit as x approaches 2 from the right of x squared minus 5. And notice that I'm not taking two-sided limits here. I'm just using the right and the left, because we already know that this and this do have total limits from both the left and the right hand side if we take the domain to be equal to the real numbers, or just a neighborhood around x is equal to 2. And the limit exists if and only if the left hand and the right hand side both equal to the full limit, so we can actually just use one-sided limits in order to justify. So when x is equal to 2 for x squared minus 5, we have 4 minus 5, which is equal to minus 1. And you can justify with the delta-epsilon definition that that is indeed true as well. So what do we have? Well, we have our one-sided limits to be equal to 11 and minus 1, and we see that these things are not equal to each other. Therefore, that previous theorem, we have that the limit as x approaches 2 of f of x does not exist in the set of real numbers. So that's how you can prove that limits do not exist using the one-hand-sided definitions to assist you. Now that we've defined limits of functions for finite values of a, and also have explored the usefulness of defining left and right-hand-sided limits for real valued functions, now let's explore what we mean when we say the limit as x approaches infinity or negative infinity for real valued functions. So just like we did with the others, let's assume that a is a subset of the real numbers with f mapping a to r, and let's assume that a infinity is a subset of the domain for some real value a. Okay, so we say that the limit as x approaches a of f of x is equal to a real number if, and you can sort of think about that this is similar to the concept of a limit of sequences, so the definition probably would be fairly familiar. If for any epsilon greater than 0, there exists an n bigger than a, the lower bound of that interval that's embedded inside of our domain, so this is equivalent in the limit sense, there exists an n in the set of natural numbers such that for all, and this is practically similar to our little n bigger than capital N, we have that the distance between our function value and the proposed limit is arbitrarily small, right? So it's practically the same as our limit definition things. The only difference is instead of n being in the set of naturals, which is equivalent to saying that n is in the naturals is bigger than 1, we just have a real value analog to that particular definition. All right, so let's see if we can prove a limit as x goes to infinity using the formal definition. So example, let's look at the limit as x goes to infinity of 5x minus 2 all over 3x plus 1. And you might want to guess what this thing is, but one should be able to show that it's equal to 5 thirds. So if you want to try this on your own to see if you can prove it formally, feel free to do so. All right, so let's see what the proof of this would look like. So what we're going to do is we're going to clearly define our functions f and our domain. So let f be equal to 5x minus 2, 3x plus 1, with f mapping the set of real numbers, except for minus 1/3, of course, to the set of real numbers except for 5/3. You should be able to show that 5/3 does not belong to the range of this mapping, but that's another exercise for another day. So what we're going to do is we're going to let a be equal to minus 1/3 to infinity. So one could just replace this with this particular a. All right, so actually let's just go ahead and do that. And we're also going to choose our epsilon to be greater than 0. So obviously we're going to positive infinity here, so this minus 1/3 isn't really going to be relevant, but we're just stating that there because at least there exists this real number a in that set of real numbers, which is all we need. So what do we have? So we have the absolute value of 5x minus 2 all over 3x plus 1 minus 5/3. So let's just do some algebra here. So let's get a common denominator between these two things. And that's going to give us 3 times 5x minus 2 minus 5 times 3x plus 1 all over 3 times 3x plus 1. Okay, so once we do that, we're just going to distribute and combine some things together. And that's just going to give us the absolute value of 15x minus 6 minus 15x minus 5 all over 3 times 3x plus 1. And let's just keep that bottom factored for now. So we have our 15x and 15x are going to cancel out with a minus 11 on top. So once we distribute our absolute values, we're just going to have that this is going to be equal to 11/3 times 1 divided by the absolute value of 3x plus 1. Okay, so what do we have here? What do we have here? So if x is bigger than capital M, right, because that's part of our definition that we need to instantiate, then we have that 1 over x will be less than 1 over capital M. Right? So this trick should sound familiar from our proofs for sequences of limits. So that means that this must be strictly less than 11/3 times 1 over 3n plus 1. 3n plus 1. Okay? And it's important to note that as long as x is bigger than negative 1/3, right, because keep in mind x is bigger than negative 1/3 in our domain, right, because x belongs to a, the absolute value practically is irrelevant here, right? So now we just need to choose our capital N, right? So we need to choose our capital M, and the only requirement or restriction we have on this capital N is that it must be bigger than our a, which for our case was negative 1/3. So technically, as long as you can choose a positive number such that it produces less than epsilon, then we're safe. So we're going to choose our n, and you can do some math in here to figure this out, but I'm going to choose my n to be equal to 11 minus 3 epsilon, all divided by 9 epsilon, because once you do that, that's going to give you your epsilon there. Right? So we have the distance between this and epsilon is arbitrarily close. Therefore, we have formally proven that the limit as x approaches infinity of 5x minus 2 over 3x plus 1 is equal to 5/3. And that's how you can prove limits for infinity, and similarly done for minus infinity limits. The last theorem that I want to leave you with is probably one of my favorites because it gives you a little bit of flexibility on how you want to formally present your proof. Because you're like, okay, well, infinity limit proofs are not too bad because it's practically similar to sequence sequence epsilon proofs, right? And if you're comfortable with that, then maybe infinity limits are for you. And if you're familiar or comfortable with choosing your delta and finding your epsilon for one-sided limits or two-sided limits, maybe this is for you. So what this theorem says is if you have a function whose domain is 0 to infinity and it maps a set of real numbers, then this infinite limit is actually equivalent to this one-sided limit. And this is an if and only if statement, so you can go literally in either direction with this. So let's actually illustrate this with a couple examples. So example 1. So let's assume that f of x is equal to 5x minus 2 all over 3x plus 1. I know we've already proven that this limit is equal to 5 over 3 as x goes to infinity, but I want to show actually how easy it is for this particular thing, provided that you have all of your algebraic limit theorems already justified or you're taking them as axiomatic. So if this is the case, then what do we have? So let's just take the domain of this to be equal to minus 1/3 to infinity, right? And obviously 0 to infinity is a subset of that, so we can technically take, actually 0 to infinity to be our domain for this function, because that's obviously a subset of minus 1/3 to infinity. Right? So we're going to be taking domain to be 0 to infinity so we can instantiate this rule. So what does that mean? So that means the limit as x goes to infinity of 5x minus 2 all over 3x plus 1 is going to be equal to the limit as x approaches 0 from the right-hand side of 5. So we're just going to replace x with minus x. So we're going to have 5 divided by x minus 2 all over 3 divided by x plus 1. Now let's do some little algebraic manipulations. So I'm going to multiply top and bottom by x, or get a common denominator. It doesn't really matter how you do it. So that's just going to be equal to the limit as x approaches 0 from the right-hand side of, so when I do that, what do I have? So if I factor out 1 minus x out of the top, I'm going to be left with 5 minus 2x. And for the bottom, I'm going to have 1 over x factored out, and I'm going to be left with 3 plus positive x. And since we're approaching x from the positive side, x is never going to be equal to 0 because x is just going to be an arbitrarily positive number. So those things are going to eliminate. So we're just going to be left with the limit as x approaches 0 from the right-hand side of 5 minus 2x all over 3 plus x. And now you can prove this in whatever way you see fit. So if you have your algebraic properties, since the only issue for this function is minus 3, and 0 is not minus 3. Technically, we can quote-unquote substitute into this because this is what we will eventually call a continuous function, right? But you can show that the limit of a quotient is equal to the quotient of the limits, provided that the bottom is not equal to 0 on its domain, hopefully, or the domain near your limit point, and the top and bottom limits both are finite and existent. So if that is the case, and that's not too hard to prove actually with a little multiplication of 1 in your delta-epsilon proof, that's just going to give you, so 2 minus x is going to vanish, x is going to vanish, and you're just going to be left with 5 over 3, which is the same exact thing as before. Right? And actually, let's just close out with another fun example, because this is actually pretty exciting. So let's do the limit, let's go backwards. Let's do the limit as x approaches 0 plus of 1 minus 2x to the power of 7 over x. So this is actually pretty exciting, right? So since we're working with a plus or right-hand sided limit, I'm just going to switch this into an infinite limit by reciprocating my x variable. So once I do that, what am I going to get? So that's going to be equal to the limit as x approaches positive infinity of 1 minus 2 over x to the power of 7x. Right? Let's just do a quick algebraic rearrangement of this. So I'm going to rewrite this as the limit as x approaches infinity of, I'm going to write this as 1 plus 1 over minus 1/2 x to the power of minus 1/2 x times minus 2 to get rid of that 2 that I introduced, and the 7 that used to be there, right? So I'm practically focusing on this minus 1/2 x term, right? So using our properties of limits, keep in mind, if u is equal to minus 1/2 x, as x goes to positive infinity, this u is actually going to go to minus infinity, right? U is going to go to minus infinity. So I'm just using a quick u substitution here. So once I do this, this is going to be equal to the limit as u goes to minus infinity of 1 plus 1 over u to the power of u times minus 14, right? And using your properties of limits that you probably already know, but this is just a composition theorem for limits, this is just going to be equal to the limit as u goes to minus infinity of 1 plus 1 over u to the power of u, all raised to the power of minus 14. And this limit we've already proven to be true. That's just going to be equal to e. So this is going to be equal to e to the minus 14 as the original limit that we presented. Right? So that's just a quick crash course through the formalities associated to the limits of real valued functions. Hope you enjoyed this video, and I'll see you in the next one. Take care.